as you know, our phosphor bronze gearing for the altitude lifter for this dish, it wore away, and we've managed to get a new sleeve to go into the thing. I've got it here. I don't know if you can see that well enough, but there's a sleeve that goes inside the main gearing, and we've managed to push this onto the um, lead screw. And as we turned it, it's gone about 1 meter. What's that, 3 feet or whatever? Um, and it's clunked into something, and we can't work out what that thing is. So we've brought some tools up this weekend to have a look and find out what it's clunking into. But it looks as though there's some raised bit of metal on the actual lead screw that we just need to file back. Once we get past that point, hopefully we won't find any more of those little snags along the lead screw, and we'll have it ready to hopefully install in the next couple of months. Our biggest issue is, as we were mentioning earlier, it's 2.5 hours to get to here. It's finding time to get up here and finding people who have got that time to come up and work on it. So being volunteers, most of us work. It's it's a bit of a tricky one to be able to come up. If we were an organisation that was purely commercial, working on the dish, it'd be done months ago. But as we don't get that time, it's taking us a lot of time just to come up. Yeah, 1 day a month is probably our best attendance for up here to do anything. So yeah, it's taken a while, but we're keen to get it sorted, and hopefully by February, March, we'll have it up and running again. Is the goal. I was hoping to have it up and running by December, but it's not looking that promising. So yeah, that's our status.
This is Dick in Honolulu. Where'd you guys get the dish and the pedestal?
So the dish itself is a Kennedy dish.
Yeah.
The telco in the 1970s was called the Postmaster General. Back then, it's now Telstra. Back then, they were experimenting with communications from the mainland of Australia across to Tasmania, the South Island. And they had 7 of these dishes, a couple set up over in Tasmania and a few in the mainland. And when the project was completed, they just discarded the dishes, and some amateur radio enthusiasts purchased them off the PNG. And the one we for pretty much 30 years and it stayed sitting all dismantled in leaves and whatnot. And as a group, our group, we decided we wanted to build a dish, and somebody happened to know that there's a chap and a amateur radio guy who's got this dish in his backyard. I'll go and talk to him. And he went and talked to him, and he didn't want to sell it. But then another 5 or 6 years down the track, they went back to him and said, "You sure you don't want to sell it?" And he said, "Oh, you can have it for $3,000." So we purchased that, and that was the beginning of a huge project to build it. The actual column, we had that commercially manufactured, as we knew we wouldn't be able to do that one ourselves.
Yeah.
So there was a bit of money put aside for putting the major infrastructure in place, and the rest of it was all volunteer work, and there was a lot of that put into it. That's for sure.
I'll bet. Yeah. Interesting. We had an identical dish at the University of Florida, and I was just happy to see the picture of yours. Ours is long gone, but I think we had 4 of them lined up over by a fence that came from the Air Force, and they were doing propagation studies with them also. And
yep.
So we used it for some solar research and a little bit of satellite tracking and stuff. Nice dish.
Yeah. We've set it up for the hydrogen line at this point.
Uh-huh.
I don't know if you've seen some of the reports that Stephen Bentley, one of our members, has put together. He's worked on improving the receiver that we got from radio astronomy suppliers over there in the States.
Uh-huh.
We purchased that and got it going, and then our member, he used to work for Philips, designing radios, two-way transceivers and all that sort of thing. And having an electronics engineering background, he went, "Oh, we can improve this," and the way he went and did a great job.
Oh, great.
Oh, yes. So that's pretty much our status at the moment. Our meeting for today is to kick the tires of this facility that we have and have a look at improvements other than the dish to do around the site and look at projects that we can focus on as priorities and what. So yes, that's us for the meantime.
All right. Hey, thanks, Phil. And if any of the guys show up while the meeting's still on, I'll put them in.
They'll probably just walk in behind me here and just join. I've got Mitch here, best carpenter. He's sitting in, listening in. So,
all right. Okay. Well, thanks.
Thank you.
Joe, what do you got going on?
Unfortunately, nothing. I've been rather occupied by other stuff for the past couple of months, so I've basically done nothing. I've still got my little receiver half built. The dish is still in the same state that I got when I got it, rather. So unfortunately, I haven't progressed any way, shape, or form in the last couple of months. So got nothing to report. They're still struggling with Python. I gotta say, still struggling with Python to enable stuff to actually work when I do put it together.
Okay. Well, Ted's our Python expert. I don't know if you got any questions you're going to ask him.
Yes, I do. I have got a copy of his ISRA. I'm trying to pull it apart to sort of have a look to see how I can improve my knowledge of it. But the best way for me to write Python at the moment is to use ChatGPT. So,
all right.
Well, that's kind of interesting to me. So we should talk some more about things. Sounds cool.
Well, yes, it is. I found using ChatGPT, I've actually got a YouTube video about it. The first time I actually logged into it, my background is in medical electronics, in service, a service engineer, and I've worked with CTs all my life, and CTs has always fascinated me. The imaging side of it has always fascinated me, and I decided I would use this ChatGPT to see what it could do, and it took me about maybe an hour and a half talking to ChatGPT to actually write a program that I could put on my PC. And I didn't guide it in any way, shape, or form. It came out, and I just told it was all wrong, what was wrong, and eventually it gave me a program to generate an image to deconstruct an image into a matrix and then reconstruct it back into an image again. Sorry, to deconstruct it into a raw file, as would be collected by a CT, and then reconstruct it back into an image again, which was really gratifying. I had no idea how to do this in Python, but it did it all for me. So it only took an hour and a half after I signed into it for the first time.
Well, that sounds pretty neat. I asked that you give me the URL in the chat so we can learn more about it, if you have this YouTube about it.
Yes, certainly can do.
Thanks.
Yeah.
All right. Well, thanks, Andrew. What's currently going on?
Hi, folks. Thanks, Rich. Hope everybody's going well. Um, yeah, dabbling around with a few things. Actually, that conversation there just reminded me of Lucy deconvolution. I don't know if anybody's had any experience there, but of course the Hubble telescope folks did. And one interesting thing to consider is trying to improve your maps. If you really know the characteristics of your beam very well, you can actually improve the resolution to some extent. I guess this is the technique that people are using now to sharpen photographs and the like. If you know the point spread function of your imaging device, you can improve resolution. So if you look up Lucy deconvolution, I've used it in my research to improve the resolution of spectra, or actually to try and get the underlying spectral form, knowing the spectral resolution of the instrument. So that was something kind of just reminded me of there. I'm just going to show the screen here. This might be of interest to folks, and we'll just share that. So here's a little circuit, and this is from a PhD thesis by Hilary Kane. Hilary was a graduate of the University of Tasmania in low frequency radio astronomy, and went on to work at Goddard Space Flight Centre on a number of missions, including IC3, International Sun-Earth Explorer, way back. Hilary is still active in research, and sort of I guess an inspiration for me. Hilary did her PhD a few years ahead of me, but she was doing a lot of stuff in low frequency radio astronomy, where you have the problem of noise from, say, lightning spherics at low frequencies. And I guess this can actually be of interest to anybody doing any radio astronomy below maybe a couple of hundred megahertz, because at times if you have a lightning storm nearby, you'll get impulses. And this is a minimum reading circuit here. If you switch that in, it will basically measure the baseline of your noise. And I'll chuck in the chat the link to the thesis, but it's a pretty simple circuit, a diode, a capacitor, and there's an output stage here with a transistor. And in good old days, you had pen recorders, or you had an output to a computer. So this kind of circuit here is a square law detector and an amplifier, and kind of a useful bit of gear for anybody that's trying to minimize effects of noise. And it can be noise just from local interference. It could be ignition noise or further that. So might be of interest. Actually, that thesis is kind of interesting to look at. I'll show you the antenna that was used. Excuse the scrolling here. But here's the low frequency array that we had near our local airport in Hobart, and pretty extensive use of dipoles there. These are kind of broadband dipoles. This system worked from about 1 megahertz up to, I think it was more like 30 or so, and mapped galactic radiation and all sorts of fun things down at those low frequencies. You've got to get through the ionosphere, which you can do in Tasmania at times, and that's kind of one of the reasons Great Reba came out here. In the early days, the ionospheric cutoff frequency can be quite low at solar minimum in winter, and they use that to actually look at galactic radiation way down to a few hundred kilohertz. And down there, it's pretty interesting. The intergalactic medium acts as a bit of a soup, and radio waves get scattered, and it's just a diffuse fog really low down. Anyway, I'll chuck that in the chat. You might be interested in the thesis. Hopefully, if I click on here, hopefully you still can see, now a different plot. And I've been mucking around with trying to get very high time resolution dynamic spectra. And this is actually a spectrum of a lightning spheric. And the times down here, these are in milliseconds. So we've got 20 milliseconds between these ticks here. And this is using Jim Sky's Radio Sky spectrograph software and using an SDR play, SDR, an RSP1 SDR. So I was just curious to see how fine details I could get, because I'm interested in solar bursts and Jupiter, and there are a number of interesting aspects to those at HF that you need millisecond timing for. And the interesting thing you can see about this lightning spheric is, first of all, it's kind of got an upper frequency here, sort of, dying off. This is in megahertz upside here, so it's an 8 megahertz chunk. And that's just simply the ionospheric propagation. But you can see that there's some dispersion, and there's also a drop-off in the kind of maximum frequency. And so some of that's ionospheric dispersion, and some of it's just the fact that the spheric is actually doing a hop off the ionosphere at oblique angles. And yeah, you can kind of see, there's another one here that's got some similar things, and they vary, depends where the spheric is. So there's a bit of interesting physics in just the propagation of lightning, kind of using it like an ionosonde, because or an oblique ionosonde, you're kind of using an impulse over a wide range of frequencies to look at ionospheric propagation over a range of frequencies as well. We don't have any idea necessarily where the lightning impulse is unless you can locate it with a timing array, such as, there's a bunch of different networks around. The Willen Worldwide Lightning Location Network uses time of flight to get the location in different receivers. So that was kind of that one, and I think I've got another one here, actually. I think it's this one here, just again, sort of continuing on with Jupiter observations. Jupiter's quite good at the moment, at least for your Northern Hemisphere folks. It's a bit low for Southern Hemisphere, but I just keep looking in at Jupiter, and one of the interesting things is just how variable the emissions are. And Radio Jove, folks get into that. Worthwhile, there's more to it than just sort of saying, I guess I've got a Jupiter observation. If you keep monitoring, you'll see all the variability. And some of that relates to the volcanic activity on the moon Io. So I encourage people to be observing, and I've been trying to compare my measurements with other folks at different locations, because the Jupiter bursts are quite narrowly beamed, and you'll actually see different effects at different locations. So that's me. Thanks.
All right. Good stuff on
In the middle.
now, did you put that lightning or I'm gonna call it a lightning arrestor or whatever circuit in your Radio Jupiter equipment?
Yes, yeah, got to be a bit careful with lightning. You don't want to get your gear blown up. So yeah, take precautions.
Oh, I was talking about that circuit to reduce the. Well, that
yes,
too,
right.
But.
Oh yeah, certainly. Sorry. No, I haven't implemented that actually, because I actually find lightning kind of interesting. So, but I do. What I do is I actually do that in software. You can actually do all that in software. If you sample quick enough, of course, you can measure the minimum. You can actually emulate that circuit in software, but it's easier to do in hardware, of course. But you can actually do that in software. So I tend to sample really rapidly and try and measure baselines like that. I do that with my VOF gear. And there are some other things you can do in, I guess, say Spectrum Lab. If people are using Spectrum Lab, there's a noise blanker in there, and various other things to get rid of impulsive noise.
That minimizing circuit reminds me of Jansky. He had noisy cars driving by, sparking stuff, and so his data was actually the bottom of all his measurements there.
Yeah, that's exactly what that does. That's right. Yeah.
So
Actually, the person
it's been a problem for a long time.
the person that circuit is attributed to is actually Pawsey, who was one of the pioneers in Australian radio astronomy, and wrote Reber, who was the, kind of, well, they say the father of radio astronomy. Karl Jansky sometimes gets that moniker. Reber and Pawsey had a discussion in about 1948 or something and came up with that circuit, and but it's attributed to Pawsey, and his name carries on. He's the square kilometre array that we're building in Australia. The centre that does the supercomputing is the Pawsey Centre.
Now, would that work on when I do meteor detection? I get a lot of lightning hits on that. Would that work on that? Or would that just cancel out the meteor?
Yeah, it'll cancel out your meteors, I think. Yeah, that's a problem. I have the same problem with my meteor system. I haven't quite. Well, I'm using Spectrum Lab, and I have tried the noise blanker. Hasn't quite helped, but I think I've got to do a software solution which is looking for broadband noise as opposed to narrowband meteor pings. Actually, the other thing I just wanted to mention too, I'd forgotten, is if anybody's had a go at Grafana, look up Grafana, which is an open source way of, plotting up data, time series data mainly, but you can have a web presence and just have things automatically sucking up all your data and displaying it online. We use it now extensively in our organization for our new ship. A lot of data streams on that, displaying it, and also down at our Antarctic stations for just displaying our atmospheric data so we can keep a check on it. But I haven't really got into it, but it's pretty powerful, and it could actually be quite a useful thing for the community here to just see what other people are doing, but even a way of sharing data, not to usurp Ted's great work, but just so you can have a look at what's happening kind of in real time.
In the chat, I put Grafana Labs. Is that the right guy?
Yeah, that's the one. Yep.
Oh, great. Yeah, that might be useful. All right. Any questions for Andrew? All right. Well, thank you very much.
Great.
Let's see. Helen.
Oh, I'm here. No, I really don't have anything. I've just been reading mostly this last month.
Okay.
Thank you.
All right. Preston.
No, I don't have anything this time either, but one day I'm going to surprise you and actually have something.
Well, you got a pretty good sized dish, I think. Yeah. Okay. All right. Richard, how's Hawaii? And
Hawaii is great. The weather's great. The RFI is terrible. So unfortunately, I'm not able to do any Jupiter work here. I am doing a little bit of work up on S-band satellite tracking, but that's about it. So I enjoy these sessions you're holding.
wow, great. Great. Yeah, especially Andrew's Jupiter stuff. I saw you pick up on that stuff, huh?
Yes, I did. It looked really good.
Okay. Robert Lucas, I know you got your solar eclipse stuff. I don't know if you want to do a quick brief on some of the stuff you've been doing.
Well, for some reason, I didn't think it was going to be necessary to do that one again.
Well, you don't have to. I'm just
Yeah, yeah, that's okay. Yeah, no, nothing really new in the last week except parts are coming in for the interferometer, but interesting comments about that. Nothing really. All I know is that Roger Heap isn't available. He's off doing his I don't know, what do they do? Some kind of plays or whatever whatever he's doing. So he's not doing much right now. Haven't heard from Michael Samirsky for a while either. So as far as we're concerned, not much is really going on.
Oh, okay.
We'll leave it at that.
All right. Thanks. Nathan.
Hey, yeah, so I've got a few things going on. Still got the pyramidal horn set up and taking some measurements, trying to clean up some of the data. I had a change in a waveguide and it changed my data output and it kind of looks a little funky. So I'm going back and hitting those elevations again to get some cleaner data. Should be done in about 2 weeks, something like that. And then hopefully I'll have more stuff to publish on shoes and kind of do a general report just to show what you're able to do with, Home Depot hardware and freeware Python package from Ezra and everything. So I'm pretty excited about that. Got a second antenna, working on it, trying to get it dialed in. It's the no-elect grid antenna, that trying to set it up so I can do longer, more detailed studies with the pyramidal horn. It's so sensitive to the weather. I don't want to leave it out all the time. So with this, hopefully I can leave it out and take 5 days or 6 days per elevation instead of just 1 day is kind of what I'm doing now. So I do have a question, and I think my shoddy fabrication skills derailed the conversation on the forum. But with the grid antenna, let me share so everybody's aware of what my lingo is. Share. So I've got that grid antenna there. Sorry, my dog's about to go haywire. Got this grid antenna and I've added this shielding there to keep the ground noise from hitting the waveguide. And I'm really curious, how do I calculate? So I'm trying to back up a step. I'm going through the fundamentals of radio astronomy, and I'm reading through this and trying to get a better understanding of how what kind of resolution, angular resolution, what type of sensitivity my scope actually might have, so I can actually make sense of the data that I'm collecting. And one of the questions I had was, how do I calculate, like if I wanted to calculate like the angular resolution, full width, half max beam width and stuff like that. How do I calculate that for something that's not a complete circular antenna? With this, it's kind of that, I guess it's probably about half of a parabolic shape. So I'm not really sure how to calculate that.
I'm thinking that's probably the key. If it was round, you could calculate that number.
Yeah.
And then you take some fraction of it that's missing and subtract it. How about that?
So just kind of do it like a ratio kind of a thing.
That's close enough for our work, I'm thinking. Yeah.
Yeah, I may give that a try and just see what kind of numbers it spits out.
Yeah. So Ted, can your software actually measure that when he takes data?
My software compares a signal that has hydrogen to something that doesn't have hydrogen. And if you don't give me that reference signal, then I use the first sample and multiply it for every one of them. So I'm always doing a relative power measurement from hydrogen to non-hydrogen. And I really don't care what the value is that you're particularly receiving. So my software currently is not the right stuff to use. My Ezra software is not calibrated. It is only relative to itself. Does that help?
Yeah, I was wondering if they could, if you could do some kind of a sun drift scan or something. That might work.
It gives you a number. You could, if you're actually talking about calibrated measurements, really SDR Sharp is still the way to go. I'm thinking I should come up with yet another software program in there called like Easy Cal, which helps you calibrate your signal to a real number that you're receiving. But I'm not there yet.
Is that something you could, if you had like like I'm using the Sauber H1 Premium, so you could or the bare bones, I mean, and so it's got that 50 ohm resistor in it. Is that something that you could possibly use to compare it to?
EasyCal knows how to talk to that real nicely. If you look at my hardware number
Mhm.
2 PDF, it talks about that. And we've talked about PC boards between us. Uh, so, yeah, you could measure it compared to that. But what is that? I don't think it's 273 degrees Kelvin. I think
Probably
it's
close, but
something
not quite.
else. I think it's some fraction of that because I find it about 60 degrees is the same thing as the sky. So it's not hot um, and it's not as cold as the sky. It's kind of in the middle. So I'm confused what it actually represents, but it is constant. It's great to compare relative measurements to. So I like that part. You get that with the bare bones version, not the one that's in a metal case. So that
Yeah.
I prefer the bare bones to add more circuitry on top of it. But we're back to calibration. I just don't know absolute numbers.
Okay.
Well,
Nathan,
I'll
listen.
play around with those numbers and see what it can come up with the ratio to the actual effective surface area or something. So
Yeah, we can change things around. If you look at the ant signal, then yes, you're actually measuring a number. But my software goes on talking about relative stuff after that.
mhm.
We can talk more privately about all those details rather than boring the group here.
Yeah. But hopefully after I get this up and I'm starting to take measurements throughout the winter, then I can I want to start working on the pyramid again. I want to start doing some data collection and some reporting to show what type of variables do you set up to get really good clean data out of that. Because right now I'm just kind of swinging in the dark, you know, 1 day drift scans and how long between reference measurements and everything. So I've got a kind of a DOE kind of a setup that I plan to do after this. It'll probably take a few weeks to do, but hopefully I'll have that ready and maybe we can talk about that in December.
DOE stands for Department of Energy. What do you think it stands for?
DOE is Design of Experiments from Six Sigma.
All
It's
right. You got to
it's a way
educate
to-
all of us then. That's good.
Yeah, it's used when you have multiple variables and you don't know. You want to see how all of them mix together instead of just changing one. You can change multiple and do that. It's a statistical process.
Excellent. Lead the way. Help us out.
Nathan, you know, your original question of the beam width, it kind of looks like the beam would be elliptically shaped. You know, so you just got two different diameters, one in this picture at least, vertical and one horizontal.
Oh, that's right. Instead of assuming it's circular, assume it's elliptical and it's running at some sort of relative to the plane.
Right. But I have no idea what the shielding screening around the, you know, extending the perimeter of the dish is. It's going to have some effect, you know, because some of the waves are going to be in phase and some will be out of phase, and how it enters the feed. So I think it's going to be really hard to precisely calculate what you have.
Yeah, I'm looking to get close, but actually what the shielding is just a aluminum door screen. And this is an idea from Alex Pettit.
Right.
So that with that grid antenna, you only get the vertical polarization.
Yep.
And so first it covers up that antenna, and so it does now it kind of gives you all the random polarization, but then
Right.
extended over it is actually there to keep ground noise from coming back. It really reduces the signal noise quite a bit.
Yeah, I understand how that works, but it probably also affects the incoming signals from wherever you're looking with the dish. But some of that's going to get reflected back into the feed with unknown phase because of the distance to the reflecting screen.
Yeah,
Okay.
I would have assumed that screen would be more of a vertical thing to the surface of the dish rather than the continuation of the dish to prevent just that, to prevent the reflection from the shield. So it acts only as like a Kumar choke rather than a part of the dish. I might be wrong there, but that's sort of my instinctive reaction to it.
Yeah, I set up the waveguide. I'm setting it up relative to the actual size of the grid antenna itself, not based off of any of the shielding there. So
Right.
hopefully I don't get too much interference from it. But my SDR for this one took a dump, so once I get a replacement for that, then maybe I can actually start collecting some data.
So is that a metal rod up through the center of the feed?
It is. And this started our discussion because I was using a quarter waveguide for this one, and talking to Alex and the team, that's going to affect the measurements too much. It's just going to it's going to affect it too much. So now I'm modifying it to a full loop waveguide, using a full 21 centimeter loop instead of using a quarter waveguide.
I see. The one that Alex uses.
Yeah.
Yeah.
So I got a new cake pan today. I'm building that one. And if I can't get that one to work, then I'll start working on building a structure to hold this thing above the antenna.
Right.
I wonder if you could have that central pole just offset by 3 inches and go up the side.
And that's something I thought of. I have to figure out a way because if I offset it the way that this mounts with that,
you'd
that
have to do
centerpiece in the
something at
mount,
dish level with a plate or something. But
yeah, I'd have to come up with
good luck
something.
in all these things. It's just easier than 4 poles coming up from the sides.
True that.
Yeah, you can do what the satellite folks do and have like a Gregorian feed too, so it's kind of well off to the side. Perhaps not helping here, but some folks that I know have done things like this is not quite the right frequency, but use geostationary satellites just as a point source, done some drift scans on those. Or, if you're at sort of ham frequencies, you can find somebody with a transmitter in the far field and on a hill or something and scan that. I've seen some people do some dish characterizations using that kind of approach.
Okay. Options. I like it. But other than that, I'm just tinkering in the dark after the time change. So
You get it. Okay. Any more questions, comments, recommendations for Nathan? All right. Keep plugging. This is really good stuff.
thank you.
All right. LBV. I'm not quite sure who you are, but come online.
You don't know who Lester is?
Oh, Lester. Okay.
I see I need to amend that somehow to add the call letters. This is Lester in transit to 6 Yankee 8 Lima Victor. There will be no Sarah active monitoring while I'm on the beach, but you can catch me on 17 meters.
All right. You got any?
Have I confused everybody totally?
Yeah. You got any updates on the 6-meter beacon project?
I was getting the test transmitter to go to chip ready, but the weather turned too cold. So I think getting the test transmitter to chip will have to wait until springtime.
All right, you want to go over what the plan is for that?
Well, the immediate results, as I published, is that the baseline design that we were talking about, that is omnidirectional antennas, 100-watt beacon transmitters, isn't going to cut the mustard link budget wise. But there's still a few that are not convinced of that. It says that I need to try some more local paths. So that's from West Virginia to chip in Northern Virginia would qualify as a decent local shorter path. So we'll see if we get any results with that. But we've had great luck getting lots of data from the folks that used to be the Maritime Coast Station in Mobile, Alabama. They've got the whisper signal, or not the whisper, I forget the exact name for it. Anyways, it's the one that Joe Taylor designed specifically for meteor scatter in parallel with 2 CW beacons, so we can see the results for both. And I can see that signal, which is transmitted with considerably more than 100 watts and considerably more gain than an Omni antenna. I can see that with a 4-element stepper, but I cannot see it with a dipole. So that's the reason for my first cut, that I don't really think 100 watts Omni to an Omni receive is just going to work. But we'll progress forward with a shorter path for the beacon CW signal to see if I can detect it Omni to Omni, or a dipole, functionally the equivalent of an Omni.
All right, and for anybody who doesn't realize what we're doing is the goal is that Sarah would like to put beacons at least across the U.S. and then extend that farther, maybe, so that since our analog TV analog channels went down, there's no way for us. There's no beacon for us to see meteor scatter with. So we're going to see if we can figure out a good beacon and Lester's working on that. And if we get this beacon working, then we're going to duplicate it so that the entire U.S. is covered for beacons for meteor scatter. And then we'll see if we can put that somewhere else in the world too.
And part of this is not simply to detect beacons. There's enough of those VHF transmitters still around that you can detect beacons all you want right now with simple antennas. But what we're really hoping to be able to do is use time of arrival techniques and precise frequency techniques to do some sort of geolocate on the meteor. And that would involve a fairly large network of transmitters, which is why we want to keep them cheap and simple.
All right. Any questions for Lester? All right. Hey, thanks. Don. I think you're the last person.
Yeah. Actually, I have nothing more in particular. I did send a little blurb to the Sarah listserv about making aluminum antenna stuff to use this Nalox or Nalox. Anyway, it's stuff that you use for aluminum to aluminum and aluminum to copper to keep the oxides from forming. Because
your message was noted, and as soon as I get back, I'm going to go buy a tub of it.
Yeah, actually, it comes in a little squeeze bottle. Don't get it spread around because it's horrible stuff. It's sticky and messy, but on the other hand, it'll sure keep the oxide joints from becoming diodes, which a lot of them do. But outside of that, I don't really have much of anything.
Okay. Anything else? Okay.
I
Great.
got some news.
Oh, go, Ted.
Okay, the audio's set. Let me share a couple things, just the latest news I've been playing with. There was an idea that I could make cheap antennas and maybe make many of them for hydrogen study at 1420. So I came up with this PVC pipe. You put a bunch of wires on it. You got a little thing for as a driven element. Sure enough, you can receive 1420. Now that they're cheap instead of lots of expensive discs or big things, why not make a bunch of them? Wouldn't it be fun to make an interferometer? Well, that requires fancier receivers and stuff. But if you just kind of add them together, you get an adding interferometer. I think that's another word for an antenna array. So that's a big fancy words for an antenna array. But these individual antennas have big beam widths. If we had an array, perhaps they could interfere properly so that we get a small beam width out of the whole array. Okay, that's good. The problem with this is they kind of blow around. They're rather big. The spacing that you really need to get this proper interference is pretty close, and yet these are pretty big. So that's kind of awkward. What if the antenna was smaller? Okay, so this is as far as I've gotten. This is 2 days ago. A bunch of aluminum discs of the right size, spaced at the right places on an all-thread quarter-inch stock. And at one point in between, you have a connector on the back, the reflector, with a little wire off to the right spot on the driven element, the next element over from the right. And I don't know if it works, but that's as far as I've gotten. I talked to Nathan a little bit about this by email. And so, Nathan, here are the pictures so far. So we'll see if this really works. There's some things I need to adjust, but if you want to come play, come play. It would be great fun. Other folks have used this before. Wolfgang, our leader in Germany, has come up with this page where he talks about all kinds of things. And the last one down here, this PDF, is kind of a summary of many different kind of antennas. And he calls this a patch Yagi. And it's kind of in the middle of his list of results. So it's not the worst and it's not the best. So it's might be passable to get 1420. So I'm rather encouraged by that part. What can we do? Can we make an array out of these? They would be sturdy enough that you could bolt them onto a 2x4 east-west and at the right spacing and maybe get it to work. Anyway, that's where I'm working on so far.
It should work, Ted.
They've made dead spring antennas and stuff, so yeah.
Yeah. One sneaky point that I picked up from patch antenna sort of practice is to find out where to stick the point of contact with the driven element. If you imagine the center is 0 ohms and the outside edge is 377 ohms, right? You do a linear interpolation at 50 ohms. That's where that little wire goes.
Okay, I like that. So if I'm wrong,
that's a
then I'm
good place
just wrong in SWR resistance.
Exactly. That's apparently is a good place to start. I get this from who? Oh God, I've forgotten where it came from.
I kind of understand the physics. Those are the two extremes. It's got to be something in the middle.
Yeah, 377 ohms is impedance in free space.
As I move that contact point in and out on a radius from that all thread, What's
Yeah.
it doing to the reactance? I suppose I'm spinning around the Smith chart.
Well, actually, that's the impede. That's 377 ohms is the impedance at the outer edge. So zero is zero ohms impedance, and the outside edge is 377 ohms impedance, not resistance. And so it's
Yeah.
50 ohms is where it looks about like where you have it, roughly speaking.
I took another design from 2.4 gigahertz and simply put a multiplying factor on it.
Yeah,
Make it so much bigger.
Yep, that's as good a thing to do as any. It maintains a linear relationship until it gets too small and falls apart. But
okay, Don, let me push you harder. What happens if I put these things near each other? I got 2 or 3 of these things. How close can I get? What are they going to do?
Well, you want to keep them. You want to keep them on the order of a wavelength apart or a little more.
No, I want interference. I want them closer than that.
You need to look at what the quad arrays use for moon bounce.
Yeah.
Spacing used there.
Yeah. That's a good place to start. Yes.
Is that some magic quarter wavelength or something?
I forget whether it's a quarter wavelength, but it's a very well-defined set of geometry. I mean, the moon bounce guys go for every 1/10 of a dB, so
right.
They're a good point to start.
And this would be at 6 meters or 2 meters and such?
432 or even higher. You don't usually have enough room for quad arrays at below 2 meters. But of course, the ultimate is the 16, the 4x4 array.
Right. You need a lot of real estate, and you hope it lasts through the storms. Yeah.
Yeah, Ted. Okay. What I've heard is that you don't want the effective areas of the adjacent antennas to overlap. So you take the gain, if you know the gain, and convert that into effective area, and then space the antennas so that the effective areas don't overlap with each other.
This would be an equivalent area for what kind of antenna?
Any.
A dish or what?
Any kind.
Any antenna.
Yeah.
In other words, the parabolic gain equation for 100% efficiency.
Parabolic. Okay, so like a dish. All right.
If I remember correctly, the relationship between the gain and the effective area is that the gain is equal to 4 pi AE over lambda squared. And that AE is the effective area.
Okay. I'm pleased that this is recorded so I can go back and review it. Thank you very much, gentlemen. Appreciate your comments.
I think most of the antenna books will have the relationship between the gain and the effective area formulas in them.
I'm sure, and they probably remember more accurately than I do.
I've forgotten entirely.
So I'm dreaming of the future. It would be cool if Sarah could get a whole bunch of these metal discs as little kits, and maybe the guy goes out to Home Depot, gets his all thread and the nuts and stuff like that, and we have an easy way to make this driven element connection. You can see I'm using a bolt, so even no soldering. And so we could have even a cheaper antenna out there that might not be good, but it might give them a fever to go explore some more with more money. Anyway, I dream.
Circles of aluminum are cheap to make.
Yeah, but they're even easier just if Sarah had a kit to buy. So
yeah, I'm saying the supplier to the Sarah can make them cheap.
Oh yeah, right. Easier than me, exactly.
Are they cheaper than cake pans? That seems to be the going thing right now.
Well, you get down the basic price of aluminum, and then like the tailor, how do you cut as many circles out of your square piece of aluminum with the minimum waste? You must have seen pictures of the guys doing that.
All right, so aluminum versus copper. How big a problem is that? Or brass, maybe?
No, stick to
Money,
aluminum.
money.
Yeah.
Use aluminum or galvanized steel, zinc coated steel will work almost as well as aluminum for
I'd
this.
rather cut aluminum on my bandsaw than steel.
Oh yeah, you bet.
Well, I've been using scissors here. I suppose the thickness of the aluminum is important, but
Nope.
not for my prototype.
It's
Would
not
not think so.
It's not important, just has to be robust.
Okay, that's encouraging. If that one driven element was copper, the little wire could stick through and you could solder at one time.
The bolt
easier.
doesn't matter. The bolt is much smaller than a wavelength. Don't worry about it.
Yeah.
Well, I was thinking it's causing capacitance between the different layers there. It's a small space.
No, don't worry about it.
Not enough to worry about.
Oh, well, that's encouraging. Okay.
Just use a little shorter bolt.
Well, that's something I got to do. Off to the hardware store. Yep.
Even that doesn't really matter.
I'm thinking if I took the wire through the plate, it just would be easier construction with a bolt holding it in place. So then you could wrap the wire around a surface that you could touch instead of trying to put your fingers down in that tiny space next to the reflector. So these are the little details of construction I'm trying to work out just to make it easier for the next guy.
I think I put a ground log on it and just run the bolt through it.
That would require, well, yeah, okay, but still getting it in the right place and stuff is awkward. So I thought a wire through a hole. Okay. How about the thickness of that wire?
Whatever.
Shouldn't matter.
Doesn't matter.
Okay. These are all encouraging comments. I will find out by doing, though. Wish me luck.
You can measure the SWR with like a vector network analyzer or something like that, I presume, too?
Yeah, but do the cheap ones go up to 1.4 gig?
Yep.
Some of them do. The semi-cheap.
I think
semi-cheap. Okay.
But,
$60 rather than $20.
Yeah. What you might find is that you can actually get away with a square driven element and maybe even square reflecting elements too. I'm not sure. I'm using a square patch for my feed for hydrogen line, and I'm following one of the last link I've put in there. But you can cut the corners off and turn it into a linearly polarized system. So you might find that there are some interesting geometries. You know, it could be square with cut off corners. You might make a linearly polarized device. I don't know.
I have seen designs that have a circle but with flat sides opposite of each other. And so I think that helps with polarization. I'm not sure I really care. I'm a little concerned that if you had a squares instead of circles here, that you'd really be working with a range of frequencies. In this case, I don't want that for hydrogen.
That's right.
As opposed to maybe you were working with a band of frequencies that you cared about, because there would be a minimum diameter and there would be a maximum diameter. And I assume that you get wavelengths for each one of those.
Yeah, I think you're right. Yeah, look, the polarization is only important if you're looking maybe at pulsars or the sun or something like that, I would say.
Yeah, but for a beginner, that's not my goal. I agree.
Yeah, that's right. Yeah, that's right. But yeah, there's lots of things to explore there. Great, good on you.
Good stuff for the winter, I'm hoping.
All right.
Thanks, Rich.
Well, thanks, Ted. And since we're talking about antennas, the ARL new antenna book is published, and we have the Sarah wrote the radio astronomy antenna section of that. So if any of you guys have a chance to get that antenna book, we've got a section, and I'm sure the next version is going to have Ted's antenna in there, and probably Alex's new design. We'll just keep improving that. Okay. Any questions? All right. Thanks everybody for popping in, and have a good week.
Thanks, Rich.
Great. Thanks, guys.
See you later.
Thank you. That was excellent. Thank you.